Okay, welcome back, Physics 30s, to our next lesson in Chapter 4. This is 4.9, and today we're going to be talking about polarized light. Okay, so far we have determined that light has wave properties. We saw this by its refraction through different mediums and its diffraction through openings. Now there are different types of waves, and it's worth considering if light is a transverse wave with peaks and valleys like this, or if it's a longitudinal wave with compressions and rarefactions. Now, it turns out that light is a transverse wave, and some evidence that we have for this is that light can be polarized. Before we talk about polarization, let's talk about what light is. Light is a wave in the electric and magnetic field, also called an electromagnetic wave. And we're going to look at EMR or electromagnetic waves more in the next lessons, but let's just take a quick look at this diagram. These axes are showing 3 dimensions, X, Y, and Z. And I'm going to put on there a transverse wave, which is representing a disturbance in the electric field. Kind of remember how we used to draw field lines for looking at electric field or gravitational field? Imagine that this is showing a change in the electric field. So I could have a small field line here, larger, larger, shorter, shorter, and then I get it flipping to the other side. This is a common way to represent the electric field. And now we also have a magnetic field that is going to be perpendicular to that. It's kind of hard to show in 2D, but hopefully you can see that it's going in this plane or in this direction. And how I would draw the field lines there are coming out like this. Again, short, bigger, peak, smaller, smaller, and then going up on the other side. So combining those would kind of look like this, with one going up and one going side to side, and then both coming towards you. Kind of like that. Kind of hard to show with the hands, but hopefully that made a little bit of sense to visualize. And why I want you to try and visualize that is because the orientation of those fields is what we're going to be talking about when we talk about polarization. Let's first start with non-polarized light. I'm going to use this diagram of an eye to show kind of where you would be looking, and then this grid on top to represent what you would see if you were looking at this X and Y plane. So first, let's start with a wave in this orientation. When that comes into your eye, you're going to see it like this in the up and down orientation. Now I'm just going to focus on the electric field lines. I could put the magnetic field lines on there as well, but it get a little bit too jumbled up. So we're just going to look at the electric field. Okay, so now if I have light in the other orientation like this, that's going to look like it's going along the x-axis like that. This is starting to build an image of non-polarized light. That's where we're going to have light in all orientations. So these 2 that we saw off the start, and then a whole bunch more orientations of light. What's going to happen with polarized light is we're going to take a lot of those orientations and we're going to get rid of them. This is going to leave light in one orientation. And the intensity of this light is going to be only about 50%. And you might be thinking, that looks like a lot less than 50% of the waves we drew earlier. And you'd be right, I took away way more than 50% of those lines. And I shouldn't have, because there is a component of those angled lines that would remain. So let's take a look at this diagram to show that. When I look at the angled lines like this, those are made up of X and Y components. When I was getting rid of some of the light, I was getting rid of everything in this orientation. That would cross this part out. However, this part is going to remain. Anything in the up and down direction, which you would see here as well, is going to remain, while everything in the X component is going to be filtered out. So I'll show here on the X, Y, and Z grid that the X component is being filtered out to polarize it. And then because we keep all the Y components, that might more accurately look like this. So that's polarization of light. Light is going to move in one plane, and then it's going to have waves going up and down in the Y and side to side in the X. When we filter out one of them and leave one orientation or one plane left over, that's polarized light. So now that we know what it is, let's take a look at where we would see this. One place that we see polarized light is when it bounces or reflects off of surfaces. I'm going to draw light non-polarized coming in like this, and hopefully you can see that's supposed to represent the X and Y plane. X in this orientation, Y in this orientation. But when that bounces off of a flat surface, the only orientation of light that's going to remain is going to be the one that is parallel or in the same direction of the surface. So I would get these flat or X dimension rays coming out. Now you can still see this light, and this is actually what you see as glare if you get sunlight bouncing off of a lake or off of a windshield. Another way that you can polarize light is with a polarizer. Polarizers look like this, and they have small strings of particles either lining up in the X direction, which we can see on top, or in the Y direction, which we can see on the bottom. These are going to filter out the light that is in the same orientation as those particles. So if I show some light coming in like this, the only light that's going to pass through that one is the light that is perpendicular to the polarizer. Now I can see then the lower one, when I flipped my polarizer, I have light coming in unpolarized, and passing through is only light perpendicular to the polarizer. Now you may have heard of polarized sunglasses, and you can kind of think of them like this. These are not polarized glasses, but I think they can help us to visualize what polarized sunglasses do. They have lines like this that are going horizontal, or what I would say is in the X direction. So it's going to filter out any light that is going to be going in that direction and allow things in the opposite orientation, moving up and down, to pass through. This can be useful in filtering out glare like we talked about in the last diagram. So if I go back to the glare diagram, we saw that this reflected light was only in one direction or orientation. But if I put in a polarizer that is in that same orientation, it's going to block those out, and we're no longer going to see any of the glare. Now, fortunately, you can still see unpolarized light, so the regular type of light that we're looking at, we're still going to be able to see. You can see in this demonstration with two polarized lenses that when we line them up over top of one another in the same orientation, they let light through in that one orientation. But when we take the lenses and we turn them and make them perpendicular to each other, then we're going to filter out light in both of those orientations, and we should get a complete blackout or total darkness. I'll try and show this with this animation where I have unpolarized light going into this polarizer. Then only one orientation can pass through. If I have the same orientation of polarizer, it's still going to allow that same orientation of light through, and that's when we were able to see light through it. But if we twist them, again, the same thing happens with the first one. We filter out 50% as we filter out that one orientation. But now I've flipped my second one to filter out the remaining orientation, and I get no light afterwards. And that's it for today's video. I hope that helped you to understand light as a transverse wave and what polarization of light is. Thank you so much for watching this video, and I will see you in the next lesson.